Chemistry. Let's get started on chapter 7. This chapter, we are exploring the implications of electronic configurations to chemical bonding. So here, you're seeing a picture of the HIV molecule, the HIV protease, I should say. And you can see in the center here is a man-made molecule called a protease inhibitor. And it's got to be the exact structure to fit snugly in here like a lock and a key to stop the HIV from continuing its biological function. So once this inhibitor is in there, HIV cannot do its dastardly thing. And so this isn't a cure, but as long as you can take this inhibitor, you will not feel the symptoms of HIV and you can live a normal lifespan. So this is one type of example how bonding can help with diseases. But there are many other applications as well. Here you're seeing a new form of carbon called a buckyball. Most carbon that you know of is carbon-12 with 6 protons and 6 neutrons. This looks completely different. It's shaped like a soccer ball and has many unique and interesting bonding properties. It's actually replaced diamond as the strongest naturally occurring substance. You can actually isolate this new form of carbon from soot coming from a candle flame. What researchers can do is dope the molecule by injecting a molecule on the inside of the cage and to change its properties by doing that. Lots of experimentation going on with buckyballs. You may have heard of bucky tubes or graphene. They're in the news a lot. This is actually being researched as a kind of synthetic blood because it seems like human immune systems do not reject blood that contains buckyballs in it. Again, just another sort of cutting edge example of chemical bonding. Here's another view of chemical bonding between two hydrogen atoms. And you're seeing on the y-axis the energy. On the x-axis is the distance between the two hydrogen atoms. And if you look on the far right, the two hydrogen atoms are far away. And here is the level of potential energy. Fairly high, meaning that the molecule is not stable. Hydrogen has 1 proton and 1 electron each. So as the two hydrogen atoms get closer and closer to each other, it's a delicate balance between the attraction of the proton of one hydrogen atom to the electron of the other, but it is also being repulsed by the proton of the other hydrogen atom as well. Two things are happening, attraction and repulsion, as they get closer to each other. As they get closer to each other, we see that potential energy decreases. In other words, the molecule is becoming more stable until finally the perfect distance away is reached, which is a potential energy minimum. So at this point here, the low point, the two hydrogens are perfectly balanced with each other. In other words, the positive end of a hydrogen atom from the first one is perfectly balanced, attracted to the negative electron of the other hydrogen atom, and vice versa, and they reach this kind of magic stability. The point about this is that this potential energy minimum is the bond length. Again, the potential energy minimum is the bond length. The bond length is therefore the internuclear distance with the lowest potential energy. Just another view about how atoms combine to make bonds and an understanding of what the bond length is. Bonding theories predict how atoms bond together. They predict what combinations of atoms and compounds can exist and which ones do not. We did this on week 1. How does sodium combine with sulfur? Remember that? You write the positive charge on the sodium. You write the charge as if it was an ion. And look at chlorine. Chlorine has a negative charge as an ion. It's in group 7. Remember, the group number is the charge on the ion for the main group elements. So all those in group 1 are +1. All those in group 2 are +2. Group 6 is -2. Group 7 is -1. And the noble gases is 0. We are now going to replicate that activity using bonding theories. These theories can explain the shapes of molecules, which in turn determine their properties. We saw that with the HIV. The shape of the molecule determined its property. So if you want to stop HIV, you've got to fit something snugly in there. The basic theory is called Lewis theory, named after Lewis, an American chemist. And we represent the electrons as dots and draw what are called dot structures. These dot structures have an enormous amount of predictive power. Using these structures, again, you can replicate the activity that we did in week 1 of figuring out the formula of the compound that bonds between 2 atoms. We're going to reach the same results in a totally different way. Lewis theory has some exceptions, doesn't work in all cases, but is still used today to explain the bonding properties of many, many types of molecules. Okay, we start with the electronic configuration. That's why this is a continuation of chapter 6. And let's look at oxygen here. It's 1s2, 2s2, 2p4. And we see that it has 6 valence electrons. Remember how to count up the valence electrons. It's always with the highest number n, the principal quantum number, which in this case is a 2. And so we see 4 + 2 is 6 valence electrons. In other words, these are the electrons that will participate in bonding. The core electrons do not participate in bonding, and so we don't need to worry about them. We write the Lewis dot structure as follows. We put individual dots to represent each electron. We have 6 total. So you would put 1, 2, 3, 4 single electrons at first, and then use the other 2 to double them up. So we're seeing the 6 valence electrons of oxygen represented as a dot structure. Here are the dot structures of several different atoms according to their group numbers. And notice that when you have more than 4, if you have 4, you place each one singly around the atom and then go back and double up. So nitrogen has a lone pair and 1, 2, 3 single electrons. Oxygen has 2 lone pairs and 2 single electrons, and so forth. Now notice the dot structure of neon, a noble gas. We said from the quantum mechanics stuff that all of the noble gases behave as noble gases because they neither want to gain nor lose an electron because they have all their shells filled. So here we're seeing neon 2, 4, 6, 8. It has what's called an octet. 8 is the magic number. At 8, all atoms, with some exceptions, on the periodic table neither want to gain nor lose an electrons. This is the driving force behind Lewis bonding theory, that all atoms want to achieve an octet and will do so by accepting or donating electrons. The octet rule. So here is phosphorus, group 5, another example. Now here is helium. Helium and hydrogen are some of the examples. Helium is a duet, meaning it only wants 2 electrons around it. Same with hydrogen. So if helium is a noble gas in this sense, it has its 1s2 shell filled. It only wants 2 electrons to achieve the stable configuration and not 8. Okay. Lewis theory has 2 types of chemical bonds. One, the electrons are transferred. That is an ionic bond. And a covalent bond is when the electrons are shared. In both cases, the atoms achieve octets and reach a stable configuration. The octet rule generally applies to all main group elements with the exceptions of hydrogen, lithium, and beryllium. We won't really talk about beryllium too much in this class. For each of these, they want 2 and not 8. So keep that in mind when you're writing Lewis structures. When metals bond to nonmetals, these are called ionic bonds. We had some homework problems in one of the chapters that just asked you to assign whether a compound was ionic or covalent. It was ionic if it's from the far left and the far right. Sodium chloride, sodium group 1, chlorine group 7, a metal and a nonmetal will combine to make an ionic bond. The second type is called a covalent compound, in which the electrons are shared. And we'll see in the ionic bond, the electrons are donated. That's the difference. And they have 2 different ways of representing the Lewis structure. The attraction between the cation and the anion. The cation, if we're talking about sodium chloride, would be the sodium, and the anion would be the chlorine. And it is this attraction that causes them to form a bond. We represent this by moving electron dots around from the metal to the nonmetal as follows. So here you see potassium and chlorine. On the left is the dot structure for potassium. It has 1 valence electron. Chlorine has 7. So we can see what's going to happen here. Potassium is going to transfer its electron to the chlorine, in which case chlorine will have an octet, and potassium will have an octet as well, because it has donated its 1 valence electron, leaving it with an octet. So we represent this with an arrow, and we write K plus, because the plus comes because it's donated its electron to the chlorine. So if it's losing an electron, it has a +1 charge. Each electron is a -1. So if it loses a negative charge, it becomes a plus charge. And the chlorine is a minus charge because it's gained the electron. And notice we put the brackets around the anion. That is just general notation for writing Lewis structures, that the brackets go around the anion. So on the right here, we're seeing the Lewis structure for potassium chloride, KCl, which is the same result we achieved on week 1 when we figured out how to do the old switcheroo. You take the charge, you put it as a subscript of the other one, and so forth. We know all that. And I'm just pointing out that we achieved the same result using a Lewis structure as doing the old switcheroo that we did early in the semester. The transfer of electrons gives chlorine an octet, leaves potassium with an octet, and we form the compound KCl. Here's another example. Mg, 2 valence electrons, oxygen, 6 valence electrons. And we see what's going to happen. Magnesium is going to donate both of its valence electrons to give oxygen an octet. If magnesium donates both its valence electrons, both atoms have an octet. And we come up with the formula Mg2 plus. Make sure you get the charges straight. Magnesium has lost 2 electrons. Oxygen has gained 2 electrons to become a double minus. So on the bottom here is the Lewis structure for MgO, which again is the same result that we got earlier in the semester, but this time using Lewis theory to predict the structure, using the octet rule. Okay, here is now another example, sodium and sulfur. You're seeing the Lewis dot structures for both these atoms, sodium in group 1, sulfur again in group 6. And we notice here that if sodium donates its electron to sulfur, sodium would have an octet, but sulfur would not. Sulfur would then only have 7 electrons around it. And so we need to realize that we need to put another sodium atom. That's the key point here. Another sodium atom is needed to give sulfur an octet. And when we do that, we come up with the correct formula Na2S, not NaS. And we see again, that's written here, the brackets, we put the anion in the center, flanked by the 2 cations on either side. Both sodiums have a +1 charge, and the sulfur now has a +2 charge. Again, Lewis theory predicts Na2S, just as we learned early in the semester. Okay, those were ionic compounds. Far left periodic table, far right. Now we do the covalent compounds, and those are far right with far right. 2 nonmetals sharing electrons, not transferring electrons. That's the difference between an ionic bond and a covalent bond. In a covalent bond, the electrons are shared, not transferred. So let's talk about Lewis structures for covalent compounds. Here is hydrogen and oxygen. Oxygen 246, hydrogen only has one. And we see that we need to include two hydrogens to give oxygen its octet. Notice there are no brackets here, no charges here when writing the Lewis structures for covalent compounds, and that the electrons are shared, not transferred. So we're seeing that if one hydrogen shares its one electron with oxygen, it gets a bond there. Another hydrogen makes another bond, and we have H2O. Lewis theory directly predicts the structure of H2O. Here you're seeing another representation of the Lewis structure showing how all the atoms have either octets or duets. The electrons that are shared are called the bonding pair. They're involved with bonding, and oxygen has two lone pairs that are not bonding, lone pairs. And as we'll see in the next chapter, the lone pairs on an atom says a lot about the shape of the atom. We are not talking about the shape at this point. We are just drawing the Lewis structure, but it's important to know whether an atom has lone pairs on it, because this will become important. Instead of writing the shared electrons, we can represent the shared electrons as a line. Each line represents two electrons. One of them is coming from hydrogen, one of them is coming from the other hydrogen, and the other ones are coming from the oxygen. So this structure, this representation is exactly equivalent to this one, but we have just replaced the bonding pairs with a line. Okay, here is another covalent compound, fluorine, a diatomic. And we're seeing what happens when you take two chlorine atoms together and they share one electron each to make a covalent bond. And so as we count up the electrons, 2, 4, 2, 4, 6, 8 for this chlorine, 2, 4, 6, 8 for the other chlorine, both atoms have octets. Lewis theory predicts the existence of diatomic fluorine gas, which is exactly what you find in nature. The ultimate test of any of this is, how does the molecule actually exist? And in many cases, it exists according to the predictions of Lewis theory. Here is H2. It's a similar thing, except that hydrogen has a duet. And so here is the representation of hydrogen gas, just H, then a line indicating two electrons, one from each hydrogen, and we get H2 with each hydrogen having a duet. Okay, now we're getting up a level of complexity here. Let's look at oxygen. We know oxygen is O2, another covalent compounds. Here is the structure of the dot structure of oxygen. And when we take the two oxygens together, if we only make one shared bond, that's what's shown here, we get 2, 4, 6, and then the other oxygen atom has 2, 4, 6, 8. That doesn't work because the first oxygen doesn't have 8 around it. This is the wrong Lewis structure. Lewis structure and allows you to play around with the electrons. And what you do is you take the lone pair from one of the oxygens, say this one, it could be any of them, and you put it as a bonding pair. That is what's shown on the bottom here, this blue arrow. They're taking the two electrons from one of oxygen's lone pair and turning it into a bonding pair. In this case, you see that 2, 4, 6, 8, 2, 4, 6, 8, each of the oxygens now has an octet, and you have formed a double bond. Lewis theory perfectly predicts the existence of double bonds. In nature, in the lab, what you actually do is you measure the bond length. So if you go into the lab and you measure the bond length of single, double, and even triple bonds, the double bond has a shorter bond length than the single bond. The triple bond is even shorter than a double bond. So if you go into the lab and you measure a bond length shorter than a triple bond, that is consistent with the double bond of oxygen, a shorter bond length compared to a single bond. Experiment supports the theory. Oxygen has a double bond, and Lewis theory predicts the existence of the double bond in oxygen simply by sharing two pairs of electrons to give it the double bond. Here's just another representation showing you the four shared electrons in the covalent bond of oxygen. Okay, you may want to try this on your own, I don't know, but if we were in class, I would have you take out a sheet of paper and try this. Do nitrogen. Here you're seeing nitrogen. Each nitrogen has 5, 2, 4, 5, 2, 4, 5. We've got 10 valence electrons total. And if we only share two of the electrons, neither one has an octet. But if we take two lone pairs, one from each nitrogen, and put it as shared electrons, that's what's shown here with these blue arrows. They're taking a lone pair from one of the nitrogens and a lone pair from the other nitrogen and converting them into shared pairs. Lewis theory predicts that nitrogen forms a triple bond. And that is correct. The bond length found in nature is even shorter than that of a double bond. So by taking the lone pairs of the nitrogen atoms, you are able to get each atom with its octet. 2, 4, 6, 8, 2, 4, 6, 8. The octet rule is correct in predicting the nitrogen triple bond. So here we're seeing this is borne out in the lab, that the double bond is 121 picometers, the single bond it's 148 picometers, and when you go into the lab, it's 121 picometers, indicating that it is a double bond. This bullet here, that Lewis theory, it does predict single, double, and triple bonds, but does not explain other properties of oxygen. For example, oxygen is magnetic, and it has magnetic properties at low temperatures, and this is not explained by Lewis theory, and that's an example of why you need another theory, because Lewis theory does not predict all of the behaviors of all the molecules. In this case, does not explain the magnetism of oxygen. Need another theory for that, beyond the scope of the class, we're not worried about it. The triple bond is even shorter at 110, again, borne out in the lab. And this, for example, if we're talking about nitrogen with its triple bond, this explains something about our atmosphere, which is 78% nitrogen gas. Nitrogen is very unreactive, so it just accumulates in the atmosphere and doesn't react with anything. Again, that comes from the fact that it has a triple bond. That is why it is so unreactive and makes such a large percentage of the components of our atmosphere. So here are the steps for writing Lewis structures. First, you write the skeletal structure. The skeletal structure shows you the arrangement of the atoms. This one is the central atom, this one goes on this side, this one goes on the other side. The skeletal structure does not include electrons, but has the atoms in their correct positions. In this class, the correct positions in the skeletal structure will be given to you. Hydrogen is never the central atom. It's always the terminal atom because it can only bond with one other thing because it only wants two. It obeys the duet rule. So for that reason, it's a terminal atom and will always be on the end. Like H2O, the two hydrogens are on either side. In this class, we're giving you the skeletal structure. You don't need to worry about rearranging the atoms. We're making it nice and easy. Okay, step 2, calculate the number of valence electrons. So you know how to do that. You look at the group number for the main group elements, look at the group number, add them all up. Now, if you are writing the Lewis structure for a polyatomic, nitrate, sulfate, cyanide, all those that are on the polyatomic ions list, you need to remember the charge. It's Cn minus. The minus sign is telling you that you have an extra electron to participate in bonding. So when writing the Lewis structure for a polyatomic, remember to calculate the charge when determining the total number of electrons. You would add 1 if it's a minus and subtract 1 if it's a plus. Distribute the electrons, giving octets and duets as quickly as possible, and distribute all atoms to give the central atom an octet and octets to all the atoms when possible. If atoms lack an octet, form doublets or triplets, and do this by stealing one of the lone pairs and transferring it to the bonding region, as we saw with oxygen and nitrogen. So here's an example, OCO. Now, when we say the skeletal structure is given, this is given. You don't really care if oxygen could be the central atom here, right? How do you know? You know in this class because it's given that carbon is the central atom. So you do not need to worry about the skeletal structure. We sum up all of the valence electrons. We've got carbon is 4, each oxygen is 6, 6 and 2 is 12, 12 and 4 is 16 valence electrons to contribute to bonding. Okay, first you would bond the atoms to each other using two electrons each. Two electrons makes a covalent bond. Each atom is donating one. So this now becomes 16 minus 4. We've used 4 of them. We have 12 left to give everything an octet. And we do that here. We got 2, 4, 2, 4, 6, 8, 2, 4, 6, 8. 16 of 16 electrons is used. But we look here and we notice that the carbon does not have an octet. It only has 2, 4 around it. So that tells us that we need to steal a lone pair from each of the oxygens and put it in the bonding region to come up with CO2, which has 2 double bonds on either side. By distributing the electrons and making double bonds, we give everything an octet. Lewis theory predicts that the structure of CO2 will have 2 double bonds, and this is correct. Here is CN. Now you have to know that CN is a polyatomic. It's not a C and an N. It's CN minus, the cyanide polyatomic anion. So you need to be aware if something is a polyatomic. So when we calculate the total number of electrons here, nitrogen is 5, carbon is 4, 5 and 4 is 9, but we need to remember that it has a charge of -1 on it, and that gives it a total of 10 electrons to play around with, not 9. If it only had 9, there's no way you could give everything an octet. With 10, you can, and when you do that, then you should practice this on your own. CN minus, the cyanide anion, has a triple bond written like this. So that is how you do a polyatomic. Okay. Here is a failure of the theory. The theory fails when you have an odd number of electrons as valence electrons. If you look at NO, NO has 11 valence electrons. There's simply no way to give everything an octet. In these cases, we do the best we can. We notice here that nitrogen has a single electron dot, it's called, and we do not have everything as an octet. 2, 4, 6, 8. Oxygen has an octet, but nitrogen only has 2, 4, 6, 7. Cannot make an octet with NO. A failure of the theory. So be aware of that if you're writing Lewis structures, that the theory does not always work. Here's another exception. Here's BF3. Look at boron. Boron has 2, 4, 6 around it. A hexet doesn't want 8. Boron doesn't want 8. It only wants 6. An exception to the octet rule. You're seeing 2 examples, BF3 and BH3. So boron, an exception to the octet rule. Here's another exception, an expanded octet. We saw boron with a hexet, and look at sulfur. Sulfur has 2, 4, 6, 8, 2, 4, 6, 8, 10, 12 around it. 12. An expanded octet. Phosphorus, 2, 4, 6, 8, 10 around it. Sulfur and phosphorus are also exceptions to Lewis theory. And In more advanced classes, we would be working with expanded octets and things like that. For this class, we don't really deal too much with exceptions to the octet rule. We just want you to be able to do the basic ones. I do want you to be aware, though, that no theory is perfect and that there are exceptions. Okay, here's another, not failure of Lewis structure, but another wrinkle about it, another complexity, is if you take a molecule like OS2. You count up all the valence electrons and you get 18. And when you do play the game of shuffling the electrons around here, you see they break it down into steps. First, we use 4 to make the bonding pairs. We distribute everything around. And we see that we only use 16 of them, and that sulfur does not have an octet. And we finally distribute all the electrons around, and sulfur again does not have an octet. So we need to give sulfur a double bond. So here we're seeing one possible structure for SO2, 2, 4, 6, 8, 10, 12, 14, 16, 18. We've used all the valence electrons. Each atom has an octet. This is an acceptable Lewis structure. However, there's another one that is equally valid, and that is if you take the double bond here and put it on the other oxygen atom, the other one. There are two equivalent Lewis structures. The name for that is called resonance. Resonance. Here they are, resonance. And we draw both structures. Here you're seeing the double bond is on this oxygen atom. Now the double bond is on the second oxygen atom. And we use a bidirectional arrow to indicate that both structures are valid. In practice, in reality, I should say, in nature, the molecule is switching back and forth between each structure. You realize that Lewis structures are taking a snapshot of a moving picture. The electrons are continuously moving around and shuffling back and forth between two stable resonance structures. And the truth is that it's actually in between both of them. But you're taking, again, a snapshot of a moving picture. So the fact is, it's switching back and forth, is intermediate between both, but we represent resonance structures as a double-headed arrow. So you'll see there'll be some cases where you can do that. I'm going to go now and take a look at the homework problems and see if there's any ones that maybe you might run into trouble. So let me switch to DocuCam here. Here is DocuCam. And let me also open the homework here. Sorry. Take a minute to pull this up. I got to re-log in again. I apologize. Bear with me here. All right, I'm looking at the homework here. Here, I'll do some of these out. I don't know how many I'll do. Depends on how hard I think they are. All right. Right here is DocuCam. I'm looking at problem number 3, problem number 4. Oop. And let's do SR2 plus. Okay. I got my periodic table out here. I'm looking for strontium. There it is in group 2. And let's see. It's in group 2 with a +2 charge. And so strontium looks like this. There it is. It does not have any valence electrons because it's a 2 plus, so it's lost both its valence electrons. So it doesn't have it. It already has an octet when it's SR2 plus. That's why it makes an SR2 plus, because if it loses its 2 valence electrons, it has an octet and actually behaves just like the noble gas krypton. So there is number 4, SR2 plus. How about Cl minus? Well, Cl is in group 7, so 1, 2, 3, 4, 5, 6, 7, but it's got the minus charge there. So that's another electron. So Cl minus looks like that. And notice everything has an octet, 2, 4, 6, 8. And that is why chlorine forms a -1 charge, because if it gains an electron, it has an octet. All right. 5. Indicate the noble gas that has the same Lewis structure. So here's number 5, Se2 plus. Indicate the noble gas that has the same Lewis structure. I'm looking at selenium here. Ooh, selenium. I think that's a mistake, because selenium here, you guys see my periodic table, there's selenium. And if it's Se2 plus, that means it would be missing 2 electrons, 1, 2, and it would be like germanium, which is not a noble gas. I think that's a mistake. The other ones all make sense, but that should be Se double minus is what it should be. I put a 2 plus in there, should be a double minus. Everyone can skip 5A. Skip. Less homework for you to do. The other ones you can do. All right, number 6. Write the Lewis structure for each ionic compound. All right, here's 6A. SRO. Write the Lewis structure, it's ionic. So that means we need the bracket notation. And so I'm going to write Sr. And where is strontium? It's in group 2. It's got 2 valence electrons like that. Here is oxygen. It has 1, 2, 3, 4, 5, 6 like that. And now let's see, how can we give everything an octet? So we see here 2, 4, 6. So we see that if strontium gives both of its electrons, now this is an ionic compound, the electrons are transferred. So if strontium donates both its electrons to oxygen, both atoms will have an octet. We put the anion in brackets, O like that, and O has now gained 2 electrons, so it has a double minus. Strontium has lost both of its electrons, and so it's Sr2 plus, like this. And here is the Lewis structure for SRO. All right, I'll do one more here. Well, I'm going to let you guys grapple with the rest of problem 6. As always, let me know if you have any questions. Draw Lewis structures for each molecule. Okay. Here's number 8. I'll do one from 8. I'll do NF3. Okay. This is now a covalent compound. So we'll use the covalent notation. We'll sum up all of the valence electrons. This is fluorine. There's 3 of them. 7 times 3 equals 21 for fluorine, and plus 5 for nitrogen equals 26 valence electrons. That is the first step, summing up the valence electrons. Okay, we have nitrogen as our central atom, and I'm just going to use lines to draw bonds to each fluorine. And now we've got 26 minus 246. So we've got 20 valence electrons left to give everything an octet. Okay, 20 left. Let's see. 2, 4, 6. 2, 4, 6. 2, 4, 6. That's 18. And we got 2 left. And there we go. Just like that. Just recount 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. We have used all the valence electrons, given all the atoms an octet, and Lewis theory predicts the existence of a lone pair on the central nitrogen atom, which is borne out in experiment. So that is the Lewis structure for NF3. All right, ozone, you guys can try that. 11, do some resonance structures, and that's it. Okay, guys, I think you guys should have enough background to tackle this homework. Good luck, and take care.